So, hi everyone, I'm Yue Ning, Assistant Professor in the Department of Computer Science. It is a great pleasure to share my research in the virtual forum in the School of Engineering. So my research has been focused on machine learning and its applications in social science, health informatics, and natural language processing. So specifically, I'm interested in a few aspects of machine learning algorithms, such as transparency, interpretability, and fairness. So I study interpretable machine learning algorithms that can help human decision-making in many real-world scenarios. For instance, in computational social science, when AI and machine learning algorithms make predictions for future events, human experts would like to know the triggers of these events and why the models predict these predictions, make these predictions. So in healthcare, machine learning approaches have been developed to assist predictions of diagnosis, readmission times, or mortality rates. One critical issue, again, in these developments is how the developed models provide evidence to support their predictions. So another direction of my research is to study problems of fairness, bias, and trust issues in online media and systems. So a few examples are detecting toxic comments, mitigating identity bias made by machine learning models in those toxic comments, fairness issues in social networks, and detecting misinformation in online media. So first of all, I would like to discuss our new discoveries in this project, learning dynamic graph-based precursors for event modeling. So in this problem, we study societal events. So societal events are such as protests, civil unrests, and violent events have a few common features. First of all, there are multiple actors. Actors here means participants, like groups of people in those events, and their relations and their roles in this event development are important. And second of all, the features, such as the actors, entities, and the relations, they're dynamic and they change over time. And last, the underlying mechanism for those events are it's usually complex. So it is unrealistic to design a theoretical model and hope it will fit the problem. So thus we use some data-driven models that can take a historical period of data and as input and design and predict the future events as output. So the data used in event forecasting are a mix of different types or different forms of features. The first of all, for example, text-based features, sometimes we call like social indicators or social sensors. Those include text-based features from news articles, from social media like Twitter, or from personal blogs. Another set of data is from like graphs, like knowledge graphs. Knowledge graph is a form that to save events as shown in this figure here. So in the right bottom, this is a graph to show a set of events and the relations between the actors in those events. So each node in the graph represents an entity or a group of people. And the edges, the annotations on the edges indicate the actions from a source entity to a target entity. So the methodology, there are a variety of methodologies have been developed based on these types of data. For instance, regression methods are developed on time series features. Classification methods are studied on like text-based features like news and tweets. graph-based approaches like graph neural networks are developed on graphs, knowledge graphs, or semantic graphs. So moreover, multi-module analysis focuses on combining different forms of features in the temporal analysis or temporal prediction to enhance the prediction performance. So in general, event prediction is a popular task in many domains. So in the context of my research, I define event prediction as a task where we use various sources of data to train a model in order to predict future events that have not yet happened. So specifically, this task uses historical event data to predict the occurrence of future events. As shown in this figure here, we can see that in the historical data, there may be different forms of data you have to utilize, like graphs, text, or time series. So in one of my recent works, we propose a new framework for predicting multiple events and their participants using graph data. So we first encode the original data in two graphs. So here we have two types of graphs. The event graphs are built from structured event tuples. They are multi-relational and they are directed, and they have time steps indicating the occurrence of events. Each node in this type of graphs represents an entity or a group, and the edges indicates there's event type between two entities. So another type of graphs is word graphs. Those word graphs are built from unstructured text data. So in these graphs, the edges are undirected, and there's a weight on each edge between two nodes. So each node represents a word appeared in the text. And then the weight on each edge represents the co-occurrence frequency between two words, as shown an example in this figure. So we have these two types of graphs over time. Each time step, we will build a graph. And then in our model, we utilize these two types of graphs together. So the event graphs encode relational information, like actions from one entity to another entity, while the semantic graph, the word graph, represents the semantic context information. So one example for an event record is shown here. So the structured information includes source, which is citizen, target, government, and the action between these two entities, which is criticize. And the unstructured data is a text summary describing the event, which is also quoted here. So after we define the two types, we design two types of graphs. We design a heterogeneous graph fusion model to enhance the representations of entities from semantic embeddings. So semantic embeddings, which means the representation of words from unstructured text. And then we also design a temporal graph learning framework to infer the event occurrences and actors in the future. So the proposed model is able to identify information flow among dynamic graphs for interpretation. So if you are interested, feel free to read our papers published at KDD 20, and then another related work was published at KDD 2019. So now I'd like to switch gears to another project I'm working on, interpretable predictions of temporal health events. So our personal health events are such as hospital admissions. They are usually saved in digital health, electronic health records, EHR. So EHR data have a few properties. For example, the features in the patient's admission records, they are often heterogeneous. So they include features such as clinical notes, which is a paragraph of text. Diagnosis is a list, And then lab results can be like continuous values. Second of all, the domain knowledge in medical domain, they are usually encoded in a hierarchical structure, and utilizing the domain knowledge in healthcare event prediction is very helpful. Is very helpful in improving the prediction. And lastly, there exist complex hidden relations among diseases that are essential to capture in order to explain prediction results. So a variety of methodologies have been developed, such as regression models, survival analysis, causal inference, and deep learning approaches. So in our recent work, we proposed a new method, domain knowledge guided graph learning, to discover the hidden relations among diseases and to learn similarities among patients from their admission records without any personal features such as biometrics or marriage status, etc. More importantly, domain knowledge, we encode domain knowledge using the tree structure. So domain knowledge can help the model to rectify and curate data-driven representation learnings. And another advantage of our proposed model is it utilizes the unstructured features from clinical notes and applies an attention mechanism to learn relevant and irrelevant keywords. So it can automatically highlight the keywords that contribute the most to a prediction. And lastly, I would like to share a project that is closely related to our current situation, epidemic forecasting. So learning on propagation patterns of epidemic diseases has a significant impact on society. Research on epidemic predictions has a long history, and more researchers have explored data, including time series data such as the past infected cases, as well as social media. So in our recent publication, we present a graph neural network based approach for long-term influenza prediction. So without external information. So this model captures spatial temporal dynamics from historical data using a cross-location attention mechanism. So this work was recently accepted and to be published at CIKM 2020. And the attention weights among the locations that are learned from training the model on multiple geolocations, and those attention weights are learned using a moving window. So we can see that on the right figure of the attentions, the matrix captures the dependencies of both the geolocation distances among locations, as well as the correlations of past time series. So again, if you are interested in more details of this project, feel free to review our paper and discuss with me. So in summary, my research interests can be categorized based on data, methodologies, and applications. So to handle data problems such as multiple types of data, we have text, we have time series, we have graphs, images, and sometimes almost in most of the cases, the data are dynamic. So they keep having new labels, new features, new entities appear in the text features, text data. So I'm very interested in developing multimodal learning frameworks and few-shot learning frameworks. So another direction related to data is I'm interested in learning fairness-aware algorithms to learn from imbalanced and biased data sets. So in terms of methodologies, I'm interested in developing deep learning models such as attention mechanisms, contextual embedding methods, and graph neural networks. Specifically for graph neural networks, I focus on heterogeneous graph learning, multi-view learning, and multi-channel learning. So the developed approaches are driven by real-world applications and challenges. We especially care about the interpretability of machine learning models, evidence-based learning to identify precursors and causes to events, and active learning to involve human expert for data curation, and domain knowledge guided learning to enhance data-driven representation learning. So thank you very much for attending this forum, and I'm happy to take any questions. And if you are interested in my research, you can also talk to me. I look forward to future collaborations.
Thanks very much, Yue, for a very exciting presentation. So questions from the audience?
Hi.
Yeah, go ahead.
Hi, Professor. This is Amit. Yes. So this is with regards to the graph, okay, the word graph that was drawn, and in terms of the co-occurrence of like the words, different words which could lead to the event. Yeah. What's basically the logic or the algorithm which you think, or over the period of time, is best works best to find the co-occurrence? Because normally it's like if the sentences are long and if there are like multi sentences, the context probably gets lost. So it's like,
right. You're asking like how do we like make sure the scalability is the model can handle like large scale vocabulary?
Yes, large scale vocabulary in terms of the word, basically co-occurrence, and what's like for longer and the shorter, like do you follow the same algorithm?
So the words are extracted from the event-related news articles. So first of all, you can do a few like pre-processing technologies, like remove the stop words. And again, in our developed approach, we actually have a mapping mechanism to find the subgraph of words, subgraph from the word graphs to map those subgraphs to our event graphs. So hopefully that is something that what you are asking.
Yeah. Yeah, something.
Okay.
Thank you, Professor.
Okay, any other questions from the audience?
Professor, a quick question on the same topic. The event prediction that you are talking about, how do you see that being applied in the real world? Is it to help doctors with a prediction of a health issue, or help enforcement with issues?
So I was hoping the developed techniques can help like to assist like care providers, healthcare providers in predictions of like future diagnosis of patients from their previous admission records. So this is in the healthcare domain, but in the social science domain, we want to develop a system or framework that can help like political scientists, social scientists to analyze the event developments and figure out, the reasons and the evidence of these events.
Okay, thank you.
Okay, any other questions? Yeah, if not, yeah, I have a question for you. And it's fascinating that you can predict future events, right, from historical data. My question is, how do you use your AI model to take into consideration of infinite possibilities of unforeseen circumstances, right? For example, there could be economic factors, there could be geopolitical factors, amongst many other. And for example, even the current outbreak of the pandemic, right, could also be considered as future event 10 years ago. And yeah, I just wonder how the unforeseen circumstances would be figured into your modeling approach.
So like predicting events that have not yet happened in the past, so your model will never know from your data, right? So that's an interesting question. So I think that's definitely one of the future directions I want to focus on. Like, can you predict new events that never seen in the training data? So far, we predefine a set of categories that we want to predict, like 20 categories. So if one of the categories, like categories can describe the general topics and events. However, in our analysis of the historical data, we can project the text data or any types data into lower dimensions. So those lower dimensions actually can be interpreted as social factors like economic problems or finance problem or like political problems. So that can actually help to explain if there is a protest in the future is going to happen, what are the underlying reasons.